yesterday we went through and we looked at a set of data and we analyzed what was happening over the course of different experiments. And remember that yesterday we talked about how you could track an experiment from beginning to end, starting at time 0, and measuring concentration over time of either the product or the reactant, and then measuring the rate over which that reactant changes concentration-wise. Then we also introduced this idea that we could do individual experiments, individual experiments that started with different concentrations and measured the rate towards the beginning of the experiment to identify the initial rate versus how much your concentration impacted that rate, okay? So then towards the end of class yesterday, we were talking about if I analyze 2 experiments at a time, so always going to be 2 experiments at a time, I'm going to look for one to change in a predictable manner. So this one doubled in concentration from experiment 1 to experiment 2. And then I'm going to look for the other reactant to stay the same over the course of that, right? Because we only want one variable when we do an experiment or set of experiments. And then I'm going to observe what happened to the rate as a result of the doubling of one of the concentrations. Now, is it always going to be that I doubled the concentration? No, it could be that I quadrupled the concentration. Whatever I observe happens here should be compared to what happens here. And so for the first reactant, we analyzed that ammonium doubled in concentration, and the rate, as a result, also doubled in concentration. Then we looked at the set of experiments for NO2, where we held the NH4 constant, and we doubled the concentration of the other thing. And in doubling, we saw that the rate also doubled, right? From there, we can analyze these different pieces of information by trying to create what we call a rate law. Rate laws will always be written in this fashion, so you'll always see the word rate of the reaction is equal to some constant value, K, times the concentration of your reactants. In this case, since the rate of reaction changed in the same way as the concentration did, we say that the rate of that reaction is directly proportional to the concentration. So whatever we do to the concentration of each individual reactant changes the rate the same way. If I quadrupled the concentration, I should quadruple the rate of any of these individual reactants. So in trying to write a rate law, what we're going to look for is to write something along these lines where we start with rate equal to some constant value, and this is something we can measure using graphs, times the concentration of each of our individual reactants. Again, rate laws will look very similar to this. Always have this part for sure. And then here's where we're going to discuss what we can try and determine will be the relation of a rate to the concentration of our reactants. K is referred to as a rate constant. Now, that being said, in trying to determine information about our rate laws, what we want to try and garner from experimental information is what we call the order of the reaction. The order of the reaction is going to be one of many things. The very typical ones are 0, 1, and 2, as far as first order, second order, or 0 order reactions. We say that a reaction is first order with respect to a reactant if, like we saw in this particular set of experimental data, the concentration changed in the same way as the rate did. So a first order reaction has predictable changes, and they are what we would say equivalent. If you change the rate, you should see the exact same type of change in the concentration. This particular reaction is first order with respect to NH4 and first order with respect to NO2. When we write rate laws, there's typically a number that comes after the bracket. And it's a superscripted number. Remember that in chemistry, 1s are typically removed, right? We don't really write the 1s. But in theory, there should be a 1 here, and there should be a 1 here. If this were a second order reaction, you would see a 2 or a 2, right? If it were a 0 order reaction, you would see a 0, or the thing would just not be present in the rate law. Why? Right. Anything to the 0 power is 1. So if you have a 0 order something or other, that means that the reactant has no effect on the rate of the reaction, first off. And second off, that it shouldn't be present in the rate law. Okay, in order to figure out what the overall order of the reaction is, we add the order numbers together. So in this particular case, we would add the ones together and we would say that the overall reaction is second order. So we can say individual orders with respect to individual reactants, and we can say overall reaction order. Okay, I'm going to pause us there, and we're going to work on some practice problems.
Are we done lecturing?
No, we're going to go over and we're going to do some practice problems instead. Like, we're going to move away from this particular thing into something different. One thing I will point out to you is uploaded onto Canvas is the Chapter 14 homework set. It is broken down by section. We've covered sections 1 and 2 in their entirety at this point. You can start section 3 after we get through today as well. So be working on that on your own outside of class because it is due next week. Okay? It's designed to follow what we're doing in class. It is this thing. But it's available, so you're going to download the Word file and you're going to do your homework on a separate sheet of paper as well as in Excel. There's Excel parts of this. So you'll be spending some time working on Excel graphs this semester or this week. Wednesday. It's going to take a while for us to get through that. All right. I'm going to do that. So let's start here. We're going to look at some rate laws, determining the overall reaction order, and looking at units for rate constants. So for the first one, it says, what is the overall reaction order for each of the reactions described below? You're given the rate law, right? We see that on the far right. For this first one, we're told that it's N2O5. The fictional number would be a 1, so what's the overall reaction order here? 1. Okay? Down here, we have two things. One of them has raised to a power of 1/2, which is able to happen. So what is the overall order for this one? 1.5. Okay? Next thing says, what are the units of the rate constant for the rate law? Okay? Now, K what are the units for concentration? In brackets. What did we say was the most common type of concentration we were going to deal with? Do you remember? Moles over liters. So K what were the units for the rate of something? Anybody remember? We said that rates were going to be changes in concentrations over changes in time. So if it was a change in concentration, it would be moles per liter over time. In our particular case, time would be in seconds. Moles per liter per second. Doesn't that put seconds in the top? If I move this one over, when you divide by a fraction, what happens to the fraction? It flips, right? The unit for K is going to be in seconds in this particular case. When it comes to rate constants, the unit will change constantly. It will not be the same every time. K will change by the rate itself. Whatever the rate law is would determine units on K, is what we're saying. Okay? All right, so let's move on. Here we're given 3 experiments with 2 reactants, A and B. And we're going to do what we did before, where we're going to try to figure out what the trend is. So, when we try to analyze experimental data like this, remember what we're looking for. We're looking to compare 2 experiments where one of the reactants is held the same and the other changes predictably. Okay? So let's identify the 2 experiments we should look at for A. We want to monitor the change in A, so which 2 experiments do we want to look at? 2 and 3, says Jewel. Do we agree? Why?
That's where it changes.
Well, that's where A changes, but what happens to B? Does B stay the same or does B change? B changes. Don't we want B to stay the same if we're trying to analyze A? So what should we pick instead? 1 and 3. Do we see how 1 and 3 changes A by a factor of 2? Do we see how B stays the same for that particular set of experiments? Okay, so from A's experiment 1 to A's experiment 3, what happens to the concentration? It doubles from experiment 1 to experiment 3. It doubles. What happens to the rate from experiment 1 to experiment 3? It goes up by a factor of 4. Okay, what about for B? Which 2 experiments should we start with? 1 and 2. That's a good idea. Does A stay the same for 1 and 2? Always double check that the other thing you're analyzing against stays the same. Remember, there should only be one variable in an experiment. So if we look at 1 and 2, B goes up by a factor of what? 2. What happens to the rate? Okay. So when this happens, we need to figure out what the order is. And when this happens, we need to figure out what the order is. One of the cool things that we can do is I'm going to give you a shortcut, okay, for determining what happens. if the rate goes up by some number should equal concentration. Ooh, I gotta remember this. Hold on. Basically what happens is this number to a power should equal the rate change. And this would be your rate, or your order. So 2 to some number, let's go with x, should equal 4. In this case, what should it be? 2. So the order of this reaction with respect to A should be 2. Should work for this one as well. For B, again, we're going to use the it doubles. And the change is like a 1, right? So what should x be? 2 to what numbers comes out to be 1? 0. So you've just seen your first 0 order reaction. Okay? Make this y. This is weird, but this is the best way mathematically to determine the order of a reaction, is to take the change of your concentration to some power equaling the rate change. So if something doubled, we put a 2. The x is the thing we want to solve for, and then on the right we say how the rate changed. So this went up by a factor of 4. We see that? Okay, so now how do we write a rate law? What are the things you know you have to have in a rate law? Rate equals, I like it. Okay. We're going to do the concentration of A raised to the order, which is 2. The concentration of B raised to its order, which is 0. This cancels to become 1, right? We just talked about y. So really, the rate of your reaction only depends on the concentration of A. Now, let's test it. We can actually calculate a K given this information. So the first thing that we were asked to do, and I'm sorry, I zoomed in on this equation. Whoa. First thing we were asked to do is to determine the rate law. Did we do that? All right. Next thing is to calculate the rate constant. How can we calculate K? What do you think?
Is it constant?
It is a constant. It should be the same for any of the things that we plug in. Okay? But how do we actually calculate the number?
Put in the concentration of the wall.
Couldn't we just pick an experiment and enter the data into our rate law? Heck yes, we could. So we can plug in the rate. Let's use, what experiment do you want to use? 1, 2, or 3?
3.
Let's use experiment 3. So we're going to plug in our rate, which we were given is 16 times 10 to the negative 5th, is going to equal K, which is a value we don't know, that's what we want to solve for, times the concentration of A at that point, which is 0.2 squared. That makes sense? Calculate K. Zach says 0.004. Anybody else agree? Should have a calculator out. Yeah.
Where'd you get the 2x equals 4? Where'd you get that 2 from?
This was the double. So since this doubled,
Okay.
that's why it's a 2.
And then same for the bottom one.
Same for the bottom one. Since it doubled, that's why it's a 2.
Okay.
It's a good question. That's where we got it from. Okay, next says what is the rate of the reaction when A equals this and B equals this? How can we figure that out now that we have K? We can plug it in to the rate law. In this particular case, it asks us to calculate the rate given information. So we're going to plug in what we know. We just calculated what K was. It tells us that the concentration of A is 0.05 molar. Does B matter? No, it doesn't. Calculate the number. Let's go, let's go. Yes, ma'am?
I got 1 times 10.
It's alright, because if you look at like our choice, is A lower than 0.1? Yeah, and so should the initial rate be smaller? Or, sorry, that's B. Just remember there was one.
All right. Hopefully that's what you got. Okay. Here we go. Here's your practice exercise. You're doing it on your own. I want to see it on a piece of paper. Make sure you look at what it's asking for. It says to determine the rate law like we did, calculate the rate constant, and calculate the rate. Bye, guys. We're working on a practice exercise. This is number 14.6 on the practice problems that are posted. We're doing the integrated rate law. I'm sorry, just determining a rate law from reaction data. Hmm?
Sorry, do we have to review the process that we did in half?
Correct, because you're doing a different experimental scale. Okay?
Yeah. Negative third. Hold on. There's the data. Just remember you're doing the rate law, the rate constant, and then you're going to calculate rate at these particular concentrations.
So the last experiment, the initial rate was moles over liters.
Yes, this is the same one, remember? The molarity, the capital M is molarity.
So we need to do something with the second one this time?
I don't know, you tell me. You have to analyze the data, right? Did you figure out what the order of the reaction is with respect to the second one?
What's part C?
Hmm?
So what's part C?
Part C is to calculate the rate of the reaction, just like we did, with those concentrations. I guess the first thing is, did you figure out what the rate order is? Not quite? Let me calibrate this so I can write on it. So which two did you use for, let's just do the rate law. Which two did you use for NO to look at it change?
1 and 3.
1 and 3. So from 1 to 3, it multiplied by 2. H2 stayed the same, just make sure you double check. how does the rate change from here to here? By 4. Okay. For the second one, which ones did you use? 1 and 2. Looks like I went by 2. How did the rate change? By 2. Okay. So your next step would be to consider. Let's do this one first. So since it changed by 2, we start with the 2. We're going to say 2 to the x equals the change, which is 4. So for this one, the order is what? 2. For this one, 2 to the y, different variable, equals what? Should be 2. So the order for this one should be what? 1. Okay, so then what do you write for your rate law? Start with rate equals, yes ma'am?
Okay, I'm a little confused on why you said that for the first one. Oh wait,
Say again?
never mind.
Okay. So we start with rate equals K. And we're going to do our NO first. The order is 2. And then we're going to put our, oops. Don't know why that happened. Times our H2 to the 1. So does it stay in the equation this time? Yes, it does. The only time it disappears is if it's 0. From there, you got to calculate K. So you're going to pick an experiment of data. Can I erase like this stuff so you can see the data? These problems are also on your screen in front of you if you want. Never mind, it won't let me zoom in. Pick an experiment of data to plug in to the rate law we just derived and calculate K. Doesn't matter which experiment, should be the same over every time. Those are how the second, rate sheet.
Yeah.
Correct. Can help? Okay. Yeah.
Oh, yeah, -3 for the actual rate. Yeah.
So the rate is the thing on the far left, right? So which one did you pick? The first one?
Yeah.
So you're gonna plug in 1.23, and then you're gonna do equals K times NO2 is gonna be, or NO is gonna be 0.1 squared, right? Remember, you're plugging those brackets mean concentrations, which are what are in the table. Yep. You're gonna do 0.1 squared, and then you're gonna do times 0.1, because H2 is 1, right? Okay, so first off, you wanna do this one, right? So you wanna put a rate here.
Oh, this is.
Okay. So we're gonna pick a number from the table. Which one do you wanna use? Experiment 1, 2, or 3?
Oh, so you can pick one.
Whichever experiment you want. And you're gonna
Okay.
plug in all that data into your rate law,
Okay.
right? So when you're plugging your numbers into your rate law down here, you pick any of the experiments. So if you're picking experiment 3, you're plugging the 4.92 times 10 to the negative third in for the rate. K is your unknown. Then your concentration of NO when you do this problem is 0.2, and your concentration of H2 is 0.1. So 0.2 squared times 0.1 to the first. I will tell you that no matter which one you pick, you're going to get close to the K value. Some of them are slightly different, but it should not throw off anything. Once you know what K is, you're going to go back and you're going to plug in the values for the last part to determine the rate. For what?
For K.
Don't worry about units on K.
Okay.
My advice moving forward.
Did you say earlier that it changes all the
It
time?
changes for every single rate law. K changes for every single rate law, so don't worry about units on K. So you did 0.1 squared times 0.1, right? And then you divided. arbitrary unit. There is no right or wrong here. So that's something to know. Yeah. That number can be anything from really, really big to really, really small. Boys and girls, there is no frame of reference for K. I'm going to tell you right now, K is a constant that changes with the experiment on purpose. So your K value could be in the thousands. Your K value could be very, very small. It is experiment dependent. Yes.
So I only needed to pick one of these if I'm an 8 by 9.
Correct. To get K. Once you have K, then you can do part C.
I have 1.2.
What's up?
So, for part C.
Yeah. Okay, so let's look at your units on K, because your K is really great.
That's what I got too.
I got 1.
Which experiment did you do? Okay.
Shows experiment 2 on the NO and
It's
1
on
on
the.
I got that.
Did you use the first one?
I got 1.23.
Well, you're wrong.
I think you're wrong. The first ones.
Did you use the. Or did you get a separate?
What did you get?
Why was it 1.2? I know.
No, failure.
Oh, no, it is 1.2. Okay, so now let's look at
Point
now let's
zero.
look at that one. Okay, so it's 0.05.
What'd you get?
Is that what I
Square.
Hey, what did you get?
I think I put a point.
Yeah.
0.123.
Yep. Okay, the value of K should be 1.2-ish. 1.23, 1.21. It really depends on what you. Ah! Mistakes were made. Go back. I don't want you using the integrated first order rate law. Ignore it. Here we go. Those are your values. So K should be 1.2. Doesn't round beyond the second, doesn't round beyond the first decimal. Your rate should be 4.5 times 10 to the negative fourth. Make sure you plugged in 0.05 for NO. If you plugged in 0.5, you're going to get a value that's a little bit bigger than this. Okay? What's up? So which experiment did you pick? You picked 2. Okay, so we do 0.1 squared times 0.2. So this is the number you should have gotten.
Yes, I got that.
No, you divided by 0.003.
Oh, I put in the wrong number when I went through.
So, I mean, that could be part of it, but let's.
I don't understand why.
That's what I do. And that's what we should have covered.
Well, you see, the issue is that I special and I got that, and then I put in the wrong one.
Yeah. Cool. How did you get the right answer?
Me?
Yes.
I'm still trying to figure it out.
I haven't charged for it.
Okay, good. Okay.
Yeah, but you know that she's lying to you. You know that she knows that you're lying to her, right?
Most of your
Well,
change.
I'm trying to figure it out.
You're fine.
No,
You
yeah,
probably
figure
didn't
it.
round it the same way they did.
I'm
Remember,
trying
they
to-
used 1.2 as K, not
I'm trying to
1.2.
figure the
Yes.
You need
concept
paper?
out.
Those of you getting
Figure
about
the concept
4.6, you're still correct. Just make sure that you realize they used 1.2 for their K, you used 1.23 for your K. That's where the little discrepancy between 4.5 and 4.6 is. Yes.
Wait, what's our
You know what? I
So first off, this one is
I got the
the.
Where?
number.
What
I
is
just
your
put it in the
So use experiment one.
Maybe you should put it in.
4.6125 times 10. It's the rough half,
I
I still got it.
swear.
I know, but like, you see,
No.
I'm learning. That's good.
I think I put something wrong in here. Did you say 1.2?
I forgot to put that in the chart.
I can't imagine.
I know.
Oh,
I am.
it should have been 0.01.
I got the K, but then I forgot to do that.
So 0.1 squared is that.
Put in 0, 1, 0, 0, right now. She needs you.
Oh,
You see it? That would get you K 1.23, then you go and you plug in. So that's K, okay.
Well, so you did not. Let's talk about how you got the wrong concept. You forgot to multiply by 0.1.
So that one, I can see that I got, cause it's 4.0.
sorry, you're too much of a dumb.
I don't know what calculator did there, but I wonder if it didn't
You're the vice
record the top number.
I need to start
What you
pulling.
plan to do?
Yeah,
I
it's
don't know.
it's 4.0.
Put this top stuff in the
I want
parentheses.
to put on my resume. I'm
See what I'm saying?
president of improv club.
Get out.
Yes, I am. No.
Shows up like
That's
Yeah,
not.
'cause if you show up like.
I'll be the second most active person.
Seriously, that's like the second most active.
Considering there's only one other active person.
All right, if you're done, go ahead and open up your homework set and start. You've got plenty of problems to work on. You can start working on the first 3 in sections 1 and 2. Number 4 says I want you to make a graph in Excel. Tomorrow in class, we're going to start with class going over how to do some of those Excel graphs.
my No, it's on campus.
Okay, because here's what I think is happening. You see how you just did this down here? It doesn't recognize that after the squares, that that's part of the bottom fraction. So, it's an exercise in parentheses. So I just do it in these steps. Divided by 0.2 squared, right?
Or just hold the paper up a little bit further.
I can't see the board.
Just hold the board out a little bit.
Still, right?
You know.
I gotta double. No. We're only dropping in Excel and looking at problems that say Excel on them. That's great.
Probably
How many
have
seconds?
over here, access to your genes.
Because you used, okay. Oh, here's what's going on. You used experiment 3's data, didn't you? Is that correct?
Yes.
Okay, then the rate you should be plugging in is not 1.23, it's 4.92. You see that?
So if I use 0. Or if I use.
So if you used 0.2 for this, you were using experiment 3's data, which means you need to use experiment 3's rate. Okay? Yes. Do you see that?
I don't.
Yeah.
Okay. What's up, Mom? Did you get it?
I forgot to do the very first straight read.
This is K.
Forgot to do the very first straight read.
This should be squared though. That's a given.
How are you surviving
And then
school?
the final has to be.
You know what? It's really only this class. Sure, that's fun. No, three people are 100%. Yeah. What are you looking at?
That's the one that
Why
we're
did you
doing.
draw? Why did
And
you
then what,
draw?
and for A,
Drawing.
But why did you draw it?
Because I need
we
it.
did in the morning.
So here.
For what?
Stuff.
To predict the,
It's like a. Oh, I get it.
so
Okay.
any coefficient will be like a little bit, and any
You don't have a dick, so
of
how
the,
would you know?
of the compounds will be in the parentheses.
You wouldn't know that unless you checked
So
very
remember, it's
recent.
reactive to
Because up until 3 days ago, it's done. Push your mind way around. No. Your mind
So
is
each one
talking
will
off
be
about
negative 1/1, because there's no coefficient.
You and I both know you wanted the 6 inches to come in.
Sure, buddy.
Is equal the appearance of H2 and O2. They always equal each other, so each one is its own thing. So, I would say pressure yes is the same idea as concentration.
Oh.
I would say pressure is more related to concentration than that.
Huh?
What are we doing?
I have opened the
39.
homework set.
Cool.
I'm on 1A.
Good.
I finished.
What-
Finish it.
What is reaction?
Yes.
It was very fun. I'm sure you followed.
The rate.